in more tropic environments, we'll say, wow, what's pour point? The synthetic, yeah, it's supposed to be really good at cold temperature. That doesn't offer me any advantage. Actually, it does. It's an indicator that it is going to continue to provide you with better fuel economy than a conventional oil will, and over a longer period of time. So there are some advantages there. Another thing, when we talk about this higher viscosity creating more heat, or more friction and more heat, and how it's detrimental. This is basically an example of it. It's called the Strybeck curve, okay? All right. Don't need to memorize it or anything like that. But basically what it's showing you the different lubrication regimes and the oil film thickness and this type of thing. And the viscosity, or as compared to the viscosity of the oil. The thicker the oil, the lower the friction is going to be on there. But there's a point, and you can see down there, right just above hydrodynamic lubrication on there, where the amount of friction actually starts to increase when you start using heavier and heavier oils. And again, that's because of that additional internal resistance in those thicker or heavier oils. So it's something that should be expected. We know it's going to happen. And this kind of demonstrates how that whole thing works out. A couple of different ways of looking at viscosity from a technical standpoint. Again, we're looking at the return resistance and how we can see that. The way, when we look at lubricants, we look at it two different ways. We look at what they refer to as kinematic viscosity. And I like to think of this as what we see. How fast does it pour out of that cup? Does it just run right out? Does it have a low kinematic viscosity? Or is it like honey and just take its own sweet time to get out of that glass? Honey would have a very high kinematic viscosity to it. How do they determine it? Basically, all they're doing is calculating the time it takes for a certain volume of oil to flow at a given temperature. And I don't want to get too deep into this. The units that are derived, and nowadays the most common one is called a centistoke on there. And basically what it's doing, if we take a look at the slide here, we have a volume in this, what they refer to as a viscometer. And it's down in the lower bulb, and they will heat it up to a predetermined temperature. Then they will take a vacuum and put it on the top of the thinner portion of the tube, and they will draw oil from that lower reservoir up into the upper two smaller reservoirs. They'll release the vacuum and allow gravity to pull that sample back down into the larger bottom original reservoir on there. When the level of oil hits the line at A, they'll start a timer. And when that level then drops down, it hits the line at labeled B there, they'll stop the timer. The higher the kinematic viscosity, the thicker the oil it is, the longer time that volume of oil is going to flow from point A to point B. That's how they determine it. So that's what we're looking at there. They also look at dynamic, and this is kind of what you feel. You're on a canoe, any type of boat, and you stick your arm out and you just move it through the air. There's virtually you don't feel any resistance on that. Okay. Now let's take your paddle and push it through the water. It takes energy to push that through there because there's resistance between the water and the paddle itself. That's what we're looking at here when we talk about dynamic viscosity. Dynamic viscosity is going to give us insight as to, hey, can we move this oil around in a lubrication system? And it's going to be done at a predetermined temperature. So we're going to look at two aspects in that. In both cases, like I said, these tests are done at certain temperatures. Why is that? Okay? Virtually all of these fluids will thicken as the temperature decreases and will thin as the temperature rises. So if we have a reference point that we're going to deal with relating to oil viscosity or oil thickness, there also has to be a corresponding temperature at which it's tested. All right. We talked about the thickness of the oil changing with this temperature on it. When we look at the degree of change that occurs, we indicate that's its viscosity index. The greater the viscosity index, the greater amount of change that's going to occur. We would like to have an oil that was the same viscosity at low temperature as it was at high temperature. But we don't have that. That's not the real world. There is going to be a change. But we can, through looking at viscosities at different temperatures, in this example here at 40 degrees and 100 or 0 degrees and 100, we can see how much change is going to occur. And if the application requires use over a broad temperature range, we can see if that fluid still has the capability of functioning over that temperature range. One of the big benefits of viscosity, of synthetic base materials, is that they have this ability to function over a significantly broader temperature range. That's why they're used in jet engines. And that's why mineral oils are not. And this just gives you some indication. There's numbers related to the degree of change. If you're looking at a base material that has, let's say, like less than 100 viscosity index to it, you know it's not going to be able to function over a broad temperature range. Those with higher, you get into the low 100s, mid 100s. Those are significantly higher, have significantly greater ability to function over those broader temperature ranges. Shear is something we talked about. A shear is basically a loss in that viscosity, and it can occur for a number of reasons. We're going to talk about that in detail a little more, but that can be an issue. That is something that affects viscosity as well. What may look good on a piece of paper, as far as its viscosity and its viscosity index or its ability to function over a broader temperature range, may change dramatically during use, and a lot of that could be shear that's occurring within the oil itself. Again, we'll detail that later. Just a quick thing on viscosity grades to try to make things more understandable for the consumer. We could talk about the technical results in doing these viscosity tests. The average consumer is going to be lost. It's going to be Greek to them on it. What some of the organizations out there have done is taken that technical data and put it into a grading or range system that gives you a better or an easier understanding as to the viscosity or thickness of the oil. Because you're going to want to utilize an oil that has a viscosity that's most desirable for your application. If we look at the Society of Automotive Engineers, they have done that for motor oils. That's the SAE grade. You know, this SAE 30 and SAE 40 and so on and so forth. If an oil tests out and falls within one of those ranges, and that's the range that's recommended by the equipment manufacturer, you know you're getting the right viscosity oil. Okay? For high temperature applications, that test is done at 100 degrees C or roughly 212 degrees Fahrenheit. Okay? Again, we have to have a specific temperature for reference because it changes with temperature. We notice that 10W30, for example, what's the W stand for? That's winter grading. we're looking there at dynamic viscosity, whereas up above we were looking at kinematic. So we're looking at how does this function at low temperatures, what is the pumpability of it, so on and so forth. That's done basically depending on the winter grade they're looking for at a sub-zero temperature on there. It's going to vary depending on the grade we're looking at. Society of Automotive Engineers also have a grading system for mobile drivetrain gear lubricants. Kinematic viscosity is done at 100 degrees C. ISO, International Organization for Standardization, basically has a grading system for industrial fluids. Their viscosity grading system is done at 40. Why the difference? Because if we look at the SAE motor oil grade test temperature, 100 degrees C, it's very close to the operating temperature of the oil in a car or a truck. If we look at the ISO viscosity grade, that 40 degrees C or 104 degrees Fahrenheit, it's more closely to that what we would find in an industrial gearbox, per se. So they match the application a little bit better. American Gear Manufacturers Association, they also have one for gearbox oils. And again, because it's industrial, they do it at that 40 degree temperature. These are some of the grading systems on here. Again, what they do is they look at a range of that the test results could fit into. If whichever range it fits into, then they go over to the left here and they find the SAE grade. Okay, I'm not going to spend a lot of time on these things. We have the same thing for the gear lubricants, the J308. Here's these ISO grades on here. Again, for right now, we don't have to go through them, but their ranges. Easy thing to remember on an ISO grade, if you want to know your oil falls or what ISO grade it falls into, determine the kinematic at 40 viscosity, and all these ISO grades are plus or minus 10%. So, you know, anything that would be a 100 would basically between, or fall into a ISO 100 grade would be anything between 90 centistokes to 110s. So it's easy if you're looking at the raw data to throw it into an ISO grade. There's in-between situations in there too. Here's just some comparisons on there. We're not going to spend a great deal on that at this particular time. This I am going to make a comment on. There are different grading systems. Not all of them are directly comparable. A big one is the SAE crankcase oils or engine oils and the drivetrain fluids, the gear oils. A lot of people will say, the oil in my transmissions and SAE 90, it's so much heavier than what I'm using in my engine. Two different grading systems. An SAE 90 would actually fall somewhere between SAE 40 or an SAE 50 crankcase oil. The numbers can't be compared. We see it all the time. Okay, I think I got about a couple more slides here. Single viscosity grades. SAE 30, for example, is a single viscosity grade fluid. And they're basically formulated and designed to form at a specific temperature. Could be either high or low, but in a very, very narrow temperature range. Okay? Multi-viscosity oils are designed to function over the broader temperature range, at cold temperatures and at high temperatures. So, car and truck oils, they would likely to be wanting to be multi-grade. You get a truck driver down in Florida is bringing up some oranges in December up to northern Wisconsin, all right? He's leaving and it's 75 degrees out there. He's arriving up here and it's minus 20 degrees Fahrenheit. He has to have an oil that can function in that broad temperature range. Otherwise, somewhere in between there, he's got to change oil. If he's just running a straight 40 weight oil down in Florida, hey, when he gets up somewhere around Kentucky or something like that, he's got to change that out to a lighter viscosity oil in order to function up in Wisconsin when he gets here. And then on the way back, he'd have to change it again. So that's the nice thing about these multi-grade oils. Okay? Many base stocks naturally have this ability to function over that broader temperature range. Synthetic base stocks, that's one of their key benefits. Naturally, they have this on there. Others have to use additional chemistry to be able to function in this manner here. And let's see if I got a shot of it here. This is basically what they'll do. They'll take a very light oil, one that has the low temperature properties that they're looking for. Now we know that as the temperature increases, that light oil is going to, its viscosity is going to drop to a point where it no longer has the ability to carry the loads that are going to be present. So that wouldn't be a good deal, but it's very good at cold temperature. So they'll take that oil and they'll put in what they call VI improvers or viscosity modifiers. They add that to it. What these viscosity modifiers do is, as the oil is heated, these viscosity modifiers, they're like little springs, and they expand way out. And as they expand, they start to interfere with each other. They increase the internal resistance. And what that does is that as the temperature goes up, the internal resistance of this oil is dropping. But as the temperature goes up, the internal resistance of these friction modifiers or viscosity modifiers starts to increase. So that limits the loss in viscosity. And now all of a sudden, we have something that has good low temperature capabilities, but can retain adequate viscosity for high temperature operation. Again, as the temperature decreases, these viscosity modifiers will start to shrink and hence create less internal resistance, so we don't get a thickening of as great a thickening effect on it. It's a real neat way to do it. Just some disadvantages, we'll talk about it later. Okay, a couple of rules of thumb. When we look at base stock lubrications, the lower temperature, the lighter the oil you need. That's pretty self-evident. Anything heavier is not going to be able to pump. The higher temperature, the heavier the oil you need. The higher the load, the heavier the oil, because of the relationship between. Okay? All right. The lighter the oil, or the lighter the load, the lighter the oil you can get away with. This is something that people forget. Speed. The higher the speed, the lighter the oil you want. We see racing applications where people say, all kinds of horsepower, all kinds of heat and everything like that. Pushing it to the max at RPMs that they can run in and not blow apart on you. And everybody wants to put heavy oils in there. Yeah, they want to put heavy oils in there to carry the heavy loads, and protect against the higher temperatures and this type of thing. But the speeds are what kills it. The speed, because of that resistance, additional resistance in that heavy oil, the speed causes the temperatures to go way up. And as the temperature goes up, what happens to the viscosity? It starts going down. Okay? So you can use these heavier products, but at the higher temperatures, their viscosity is going to drop back, and that internal resistance is actually going to be a negative. Plus, it's going to suck energy. It's going to suck power. And if you're talking about racing, we're talking about fractions of a horsepower that make the difference between winning and coming in second place on there. It's the last thing you want to do. So the higher the speeds, the lighter the oil that you want to use. The slower the speeds, the heavier the oil. Okay, at this particular time, we're going to take a break.